Welcome everybody to example 9. We are still looking at page 116 of the workbook here. This is going to be one more example of using the substitution rule to evaluate an integral. In this case it's a definite integral because we've got limits, 1 to e. Okay, so as with all of these problems, we need to start out by making a choice for u. In this case, it's maybe not so obvious because I don't see a function that's inside of another one, and so we could use a little trial and error like we did on example 8 and discover that in this case, a good choice for u is to just choose it to be the numerator, ln of x. Okay, so after we've made our choice for u, we need the derivative of u, so we'll calculate du. Derivative of ln of x is 1 over x, so du is just going to be 1 over x dx. And notice that this is kind of a good sign because we got an x in our denominator, and looking at our integral, there's an x in the denominator there as well. Okay, so kind of tells us that we're maybe on the right track here with this choice that we made. Okay, and we need to solve for the dx. In this case, to get the dx by itself, it's actually easier to multiply both sides by x. Okay, so let's do that to get the dx by itself. That's going to give us x du is equal to dx. Okay, and so if we do our substituting, okay, we're interested in substituting those two pieces into our integral. We're starting from the integral 1 to e of ln of x over 2x dx, and if we substitute those pieces in, starting with the ln of x, we called that u. So we're going to get a u over 2x, and then dx, we can see from our work above, is equal to x times du. Okay, do we get any cancellation here? Well, notice that we do. We've got an x in the top and the bottom. Those x's go away. And the fact that all the x's disappeared is a good sign, okay, that maybe we made a good choice for u here. All right, oh, and let me correct my notation here. Okay, this integral that we're looking at over here has x's and u's, so instead of writing 1 to e, I should really emphasize that those are x values. Okay, just write it as x equals 1 to x equals e, so we know what variable we're talking about. Okay, and continuing here, the x is canceled, so we're just looking at an integral that looks like the integral of u over 2 du. Okay, and we've got an over 2 in the bottom. That's a constant, so we can pull that out as a 1/2. And so the function that we need to integrate is just u. Can we find an antiderivative for u? Remember that u is just u to the first, so we can use the power rule on that. We've used that formula a couple of times. The power rule says we're just going to take that power of 1, raise it up by 1, divide by the new power. So antiderivative of u is u squared over 2. And this is a definite integral, so we're going to substitute in our limits. We don't need a plus c. All right, and before we do that, we need to remember what u was equal to. It was equal to ln of x, so we'll go ahead and substitute that back in. Okay, maybe at the same time we could notice that 2 times 2 is 4, so we'll put those together into a 1/4. U is ln of x. Okay, and then we need to evaluate between e and 1 to finish up here. Okay, so let's plug in our upper limit. So we're going to get ln of e squared. There's our upper limit minus our lower limit. Substitute in 1. Okay, and we just need to calculate our numbers to finish up here. So ln of e, anybody remember what that is? Okay, ln of e is actually equal to 1. You could ask your calculator if you don't remember that, and ln of 1 is actually 0. Okay, so when we do that, we are going to get, let's see, 1/4 times 1 squared. The second term is 1/4 times 0 squared. That's just going to be 0, so we get an answer here that looks like 1/4. Notice that that's a number, because of the fact that we had a definite integral. And if you think back to what an integral represented, we just calculated the area under that curve, essentially. Just to remind you of what the meaning of an integral was from earlier. Okay, and we are done with our problem.